Hello, everyone. Good afternoon. So today we are going to talk as Kubernetes from the database out. So I'm Edith, and here we have Alastair. Next slide, please. I work for Percona, as you see the t-shirt here. I am tech evangelist at Percona. I am also part of the QA team for the Percona Everest project, and I am CNCF ambassador. We have Alastair.
Hi. So I am a database nerd. I've been a database nerd for a very long time now. What I currently do as a database nerd is that I'm a tech evangelist at Percona. I really did try to avoid this whole new cloud-native infrastructure thing for a while, but come 2018, it caught up with me. So Kubernetes has been part of what I've been trying to talk about along with databases since then. Why this presentation is really that a lot of the introductions to databases on Kubernetes start with things in the Kubernetes order, all these little building blocks, and by the time you've figured out how they build up 7 layers deep, you've forgotten why they matter to a database in the first place. So the idea behind the running order and the structure of this is to present bits of Kubernetes to you in the order you'd see them if you'd been given a managed database on Kubernetes and now needed to interact with it. So some of this is about the terminology. Yeah, it's important for database people to talk to infrastructure people in terms we all understand. But on the whole, it's just a different perspective, a different order of looking at some of these things, which is hopefully interesting, and yeah, you can learn 1 or 2 new things from.
Yeah. As Alastair said, we are going not to talk about the natural order that we already know, but we are going to start for another component. So the first thing that we are going to see is how we are going to try to see how to connect it to the database. We are going to see what is the query for the database, and also we are going to see the Kubernetes commands. Alastair has a database background. I have a DevOps background, so this is a great opportunity to match that both knowledge, and we are going to see it in the presentation. We are going to see also querying, recovering, and how when something breaks, we are going to see how to see the logs, what tools we use to see the logs, and we are going to see deploying and scaling, how we can see that kind of processes in databases, and then a time for QAs, for questions. For our environment, we have PostgreSQL cluster with 3 nodes running. On Kubernetes, we use our favorite database, PostgreSQL, the version 16.4 running on GKE. So we deployed this using Percona Everest, which is a cloud-native solution to run databases on Kubernetes, to manage and to provision. It's free, it's open source, feel free to involve and to send feedback as well.
Right, so just in case there is a prize for the presentation that gets to the command line quickest, here we are on slide 5. So if you are a DBA, you've been handed a set of credentials for a managed database on Kubernetes. What does this look like? What do we see? So we've been given an IP address, given a password. We can log in, nice and easy. Also, just by the way, since the demo gods I think are under enough pressure today, we've decided not to place any more strain on them. These are all pre-shot, obviously. If we have a look at what the database knows about our connection to Postgres, so for our process, the application name is PSQL. It's the client library. That looks right. The IP address doesn't look right. This is not an address outside. This is a private address, and we'll see why shortly. The other place that you may find some information from Postgres about its networking is where it's listening. It's listening everywhere. Everything that Kubernetes forwards to it, it's processing. And we can now see on the Kubernetes side how all of that gets to us.
Let's see Kubernetes commands, Alastair. So if we list all the services that we have in our Everest namespace, where our cluster of Postgres is running, we see that PostgreSQL PG Bouncer is there. Is the type of load balancer, so it has an external IP. That external IP is where Alastair made a connection for the database, for Postgres, and PG Bouncer is special because PG Bouncer acts like a proxy for a database. It means that instead that the applications can make direct connection to the database by one, PG Bouncer try to reuse the nodes, a small amount of nodes, so to make everything more smoothly and more simple and efficient.
So if we then just sort of look at what some of the things are behind that networking, we had a load balancer there. The networking for Kubernetes to forward traffic to a service is important because when we have multiple instances of a thing like Postgres, when we have a distributed database, when we have primaries and replicas, they need to have stable addresses. The replica always needs to know where the primary is to connect to and get the data from. So instead of workloads spinning up with new addresses every time, as would normally happen inside the Kubernetes cluster, we need a stable place to address them. That is provided by a component of Kubernetes called kubeproxy, but if you're just thinking about this with a naive networking hat on, you'd think, okay, kubeproxy gets the data and forwards it. No. What kubeproxy does is it configures the kernel of whatever operating system you're running on to do all of that forwarding. So if kubeproxy, for instance, did go away, all those forwarding rules remain. All it does is keep the kernel networking up to date and running on time. So that's great if you have an application inside the same Kubernetes cluster trying to access the database. As soon as you try to move a little bit further outside the cluster, as you would for a database as a service system, you need exposed connectivity. That's provided by the node port construct. So this will expose a port for you on every node in the cluster. It won't be that 5432 that we expect to find Postgres on, because in that case, we'd only be able to run one Postgres inside any Kubernetes cluster. It's a port that's assigned from a range. In order to now make this accessible in a way that the application expects on the right port, do all the things around balancing across primaries and replicas, you would put a load balancer in front, and it would do the health checks on which bits of the cluster to connect to, which is where we were for our example. Now, once we've connected, we need to query. If we are working with enough data, or if we're writing any data out, and we want to get to that important aspect of a database that is durability, we need some sort of storage to work with. In much the same way that on a Unix system, you'd take a device, you'd mount it to a path, and that's where you'd store your data. In the Kubernetes world, there is some persistent storage out there, called a persistent volume, and you claim it. Similar kind of idea, new set of words. Persistent volumes are not normally created from scratch, by hand. They're created automatically when a claim is made that isn't satisfied. So you will hear, or in discussion with infrastructure people, the idea of a PVC used almost interchangeably with the volume itself, because they're often only created at the point at which they're claimed. And this whole process of getting the storage in the first place is done by a set of software called the Container Storage Interface. So this is the standardization that allows Kubernetes to perform the same set of actions on top of any piece of infrastructure. One of the more interesting things from a database point of view here is that a number of the CSIs give us the ability to do snapshot cloning. So when we're trying to create replicas of a database, instead of having to copy all the data off one volume, write it back to another, we can just take a snapshot of the volume and spin a replica up immediately on top of that same persistent data. So from minutes or hours down to seconds, which is a great benefit to sysads to database administrators when building clusters or when upgrading them, which often requires rebuilding replicas. So if we have a look at what Postgres thinks about its storage, we see the storage directory is the default. So this is where we'd expect to see the storage from Kubernetes mounted. The other bits which would show more detail about where the storage was, the temp table spaces or the contents of the PG table space system catalog are all empty. So what we can see for this particular setup is that everything is under that PG data mount point, and that's where we'd expect to see all the bits from the Kubernetes cluster mounted. On the Kubernetes side.
Amazing how it looks in databases. I always wanted to know how is inside databases, what is happening. So let's see what is in Kubernetes, how it looks. So if I make a list of all the persistent volumes that I have several of them. So they are like storage, pieces of storage in the cluster. and we have in the bottom persistent volume claims. It means that we are going to try to request that storage that we have for the persistent volume, and it's going to be bound to the persistent volume through the ID of the persistent volume, you see. So all of these claims, as you see, the persistent volume claims has 25 gigabyte, right? Gigabyte, and all of them are have a storage classes of standard read-write only. Also, we have, if we select one of the pods and we inspect all the volumes of our pods, we have several of them. This is just specific for our PostgreSQL database. So if we see the main and the most important here is the Postgres data, is where our data, all the data we are going to store in the database is going to be there. The other volumes that you can see are for things like backup, like restore, that temporal files, for example. If we see the storage classes that we have for this cluster, we found three. The standard read-write only is the default one, and it depends of the cloud provider that we are managing, and also depends of the on-premise setup. So it depends of us to ask which storage class is optimized so we can run databases on Kubernetes with a specific storage class.
Yeah, so just following on from that about the particular storage classes here, what's interesting to see is that we do have an option for going faster. There is something called premium. Presume that'll go a bit faster than the standard we've been issued by default. And looking at all of those mounts into the container, so Postgres data is what we'd normally think of in the database world as persistent storage. It's a volume that we can put data on and go get it back later. A lot of those others, like the certificates, like the PG backrest config, they aren't real disk. They're read-only mounts of data that is managed by the Kubernetes cluster about the configuration of Postgres, about the configuration of PG backrest in that case, or about the certificates that these systems are supposed to use for authentication or for encryption. So Edith mentioned at the beginning of her explanation the idea of a pod. This is generally where any discussion about Kubernetes starts, and I think we've got about as far into any discussion about databases and Kubernetes as we can without mentioning the P word and explaining them in a bit more detail.
Yeah, we started explaining services, explaining others. Now it's time to explain about pods. Pods are pods of PIAs. It's a group of containers that are managing together. So they share. We can have one single pod running usually in one single container running in a pod, but we also can have several pods running, several containers running in a pod. So in this case, for our demonstration, as we see, we have several containers running in a pod, and they share the same. They can share the same storage. It means that one container can access the storage from another, and the other for the other. They can share the same networking. It means that they can talk each other through local hosts, and they are limited by the resource constraints for the resource constraints. It means they are limited for CPU and memory for the container. So if we see the Kubernetes commands for this, we list all the pods, we inspect the pod that we have there, and we inspect all the containers that we have. So in this case, we have 4 containers, for example, and the main one is the database that we see here. And we have, for example, PG backrest. So they are both 2 containers running in the same pod, and they share all the resources that I mentioned.
And the reason there, for instance, the PG backrest one being in that same pod would be important is because they need to share access to that underlying volume. Your backup process needs access to the same storage that the database process has access to. So as we start to build these distributed systems, one of the first things we need to deal with is what to do when things go wrong. In the past, we had mainframes, tandems, sequence, all of these big machines trying to avoid anything ever going wrong, over-engineered to pieces. If we move to the other end of the scale, Kubernetes tries to maintain resilience by recovering quickly and recovering automatically when things go wrong. So what happens when a particular database instance goes away is something which Kubernetes can help us with, which can be better managed than we would be able to do it manually or with many of the other automation tools. When any of those containers inside the pod fails, so for instance that PG backrest process, the process would be restarted. If a pod on the whole is unhealthy, Kubernetes will destroy the pod and recreate it. Now that process of destroying the pod, recreating the pod, may bring it back at a different address. The question for something like a database engine is that whether the same address actually lines up to the same data on disk. And there's a construct in the Kubernetes world called a stateful set for ensuring that that happens. In some ways, it makes sure that the processes you're running inside containers behave a lot more like you'd expect a process to inside a VM. It just is a lot more stable. So we end up using a lot of the same tools we do for managing HA and DR of databases in the VM world. For Postgres, it's Percona. So the Percona system knows when the primaries disappeared. The Percona system promotes the replica. There is an alternate view on this, which is if we're doing this all inside Kubernetes, if we have Kubernetes knowledge of the health of all of these components, why aren't we leaving it up to Kubernetes? And the challenge there is that a stateful set doesn't have any construct for knowing what the role of each of these pods is. It just knows that they're all there. It knows what order they need to start in. So some of the producers of operators for Postgres and Kubernetes have chosen to move away from the stateful set. They've put a lot more code into the operator, and the operator manages not only the role of each of these instances of Postgres, what's a primary, what's a replica, the promotion, but also the health of them and managing the restarting of those processes. So it's fewer Lego blocks, but more control, which is always an interesting trade-off. Now, when something does go wrong, the first place we're going to want to go and look is the logs. So knowing how they lost, where to find them, would be interesting.
Let's see about logs. So usually the databases save the logs into files, but when they are running in Kubernetes, they write the logs in a standard output, a standard error. Also, they are saved in the node. So if something happened to the node, so our logs they are gonna disappear. We can see the logs with kubectl logs and the name of the pod. And if we want to do something better with the logs, like compilate the logs across the cluster, we can use other custom plugins and other tools to help, for example, to visualize these logs better and also to give it a better format.
Right. So one of the things that probably missed one of their slides. One of the things about using a tool like kubectl and using the cluster to manage the aggregation of the logs is that we don't need to get involved in things like log rotation anymore. It's not what's the period of this log, what's the file name I need to go looking for this particular time period. The fact that they're all managed behind a single interface provided here by something like kubectl allows us to just give it a date range and go off and do as we see fit. So we see here the config on our test cluster. It goes to standard error. There is no information about log rotation, so this is all just being left up to the Kubernetes cluster to manage for us as it sees fit. And the logs at least will outlive the end of the pod. We know that they're stored somewhere more reliably.
So let's see now how it looks logging in Kubernetes. If we list our pods and we take one of our Postgres instance and we inspect the logs, we will see this, things about Patroni, for example. So when we deploy the databases for this environment, it deployed everything that is necessary already for the database. So it installs Patroni, which is going to help the database to have high availability, is what we want when we run databases on Kubernetes. So if we see there, bootstrapping from leader Postgres is trying to create a node from the backup, so it's going to try to secure high availability. Okay, we talk about several Kubernetes objects. Now let's talk about the start of this talk. So the Kubernetes operators. The Kubernetes operators are database logic that is added on the top of Kubernetes to manage and automate databases process. So for example, I can write custom resource definitions that are the main component of Kubernetes operator to automate backups, replicas, store, scaling, rolling upgrades, and all these components. And it make it efficient, and it's possible, and it's the way how we can run databases on Kubernetes, thanks to the operators.
All right, so just to then tie all of that together, I'm not going to read through the whole thing. Just one or two just important bits to talk about here. Firstly, those little things in bold are your bluffers guide. These are the terms that the DBAs need to be able to talk to the infrastructure people. Just one thing right at the top about packaging. We often hear people talk about various operators for a particular database technology. We've been talking today about Percona's operator for Postgres and about Cloud Native PG. It's not just the operator. These all come with their own set of container images that they manage in a different way with different behaviors that match up between the operator and the container images. Other than that, just say, hope this has been interesting. This is an area which has become useful now. We can sensibly use Kubernetes to run databases, but it's not quite there yet. If your thing is Kubernetes and control planes and cross-cluster control, or if your thing is databases, get involved, push it a little bit, because there is certainly still some space here that we can work on together to move it forward.
Yeah, you will come to contribute to the data and Kubernetes community. So where you are working for all these initiatives to create more standards to run databases on Kubernetes better. Yeah, I think we are on time, right?
Yeah.
Okay. Okay, thank you.
Thank you very much. Questions?
Is there a trend that you're seeing between DBAs asking for this, or is it infrastructure people asking to run the database? Who's deciding?
So it's not often the DBAs. So it may be app teams. The idea of the microservices database, that you have one database with each app inside the Kubernetes cluster, is driving part of this. At the other end, it is the database engineering teams who are trying to create standardized, repeatable, low-effort deployments for all of the app teams, and that's where we see the sort of database as a service stuff play out. Those are, I think, really the two areas there. The DBAs, unfortunately, it just happens to them.
They just want a database, right?
Yeah.
And then what's the biggest challenge with running a database in Kubernetes today? What are we missing? What's the biggest thing we're missing?
So I'd like to see the idea of the stateful set extended a bit, so that example I was talking about, where some of the operator teams are deciding stateful sets are fighting against them, and they're trying to replace all of that functionality. It doesn't feel like a good thing to me ecosystem-wise. I think the ecosystem could serve stateful workloads a little better, and then we wouldn't end up with quite as much fragmentation at the operator level.
Fair. Cool. Thank you.
Great talk, thank you. Just following up on your question, I wonder, and I know it's a little bit of a naive question, but what's the main challenge using persistent volumes over using ephemeral storage directly?
So I think it's making sure that we can get the replicas back quickly. So when we have things like snapshots, not all the CSIs provide them, but the CSIs that do, we can get a replica really fast. If it was ephemeral, we'd have to wait to move the data between the machines. That said, another area where I think it's actually the operators, it's not the underlying Kubernetes stuff, isn't doing very well at the moment, is providing ephemeral storage where it's appropriate. So in a database, you have operations that spill to disk. The sort is too big, it needs to go to disk. At the moment, most of the operators still try to put their stuff on PVs. The model of trusting that there will be ephemeral storage or testing at startup time that there is actually some ephemeral storage you can use isn't there. And maybe that actually is another area where the underlying stuff provided by Kubernetes could improve, is providing some assurances around the ephemeral storage. Because at the moment, there's strong assurances around PVs, but ephemeral storage is just kind of try and see.
Yeah, great presentations. So there are some alternatives to running Postgres in Kubernetes. Without going into details, what would you say sets Percona apart from the alternatives?
We have in this open source world there are several. Yeah, there are several Kubernetes operators. It really depends on what your necessity is. But for example, we have Cloud Native. There is in the Cloud Native ecosystem, there is Cloud Native PG, there is Crunch Data, there is Solando, and it depends the operator. If that adjusts to your business, you can start to use that. So we don't say we are the only operator. We have several, but every operator has his own strengths. So it depends, as always. It depends.
Yeah, I suppose the key area where we are trying to differentiate isn't actually on the operator. It's that layer over the top with Everest. But yeah.
Can you repeat it to the mic? Sorry.
Oh, sorry, I'm not close enough to the mic. Yeah, so I think really the key area where we're trying to differentiate is not on the operators individually. There are trade-offs there. People have made different architectural decisions, but the layer over them to give you database as a service on top of the operator is, I think, the area where we're trying to differentiate. And if anyone is at KubeCon, I presume most of you will be. We will have a booth. Come and talk to us. And a different database product we're involved with, Valky, is having a birthday party on Tuesday. So come and get a cupcake.